Hi everyone, I am Namrata Roy from University of California, Santa Cruz. I am very excited to be talking to you all about my work, which focuses mainly on searching for maintenance mode feedback signatures in typical quiescent galaxies. But more specifically, I shall focus on a very interesting sample of early type galaxies called red geysers that show galactic scale AGN driven winds. So the big question is, what causes galaxies to quench? So in this plot of number density versus redshift, we can see that the number of red galaxies shown by red points have been increasing steeply towards present time, which is redshift 0. This means that more and more galaxies are transitioning from the blue cloud towards the red sequence and are not coming back. So what causes this quiescence? So one of the most popular theories has been AGN feedback, specifically maintenance mode feedback or radio mode feedback that maintains the low level of star formation at later times. So although we do have some examples in cluster scale and in radio galaxies of this AGN feedback, we don't have that many observational evidence happening in typical elliptical galaxies. And that is where this work comes in. So the goal is to find evidence in typical red sequence galaxies. So my work uses data from many surveys and instruments, but I wanted to specifically mention the MANGA survey. So MANGA is a part of SDSS-4 and it is an IFU survey that looks at nearby galaxies. So using MANGA, we now have spatially resolved information across each galaxy and for thousands of galaxies. And while looking at all this data, we found this interesting sample of early type galaxies that look something like this. So in the right, we are looking at spatially resolved 2D map of H alpha equivalent width in an early type elliptical galaxy. Equivalent width is basically like flux, so this map is basically showing you the spatial distribution of warm ionized gas. And we can see this bisymmetric or biconical feature that looks like a fountain or a geyser. That's where the name red geyser came from. And not just one, we have many such examples, and all of them show this bisymmetric or biconical feature in the warm ionized gas map. However, these, if you look at the optical image, they all show perfectly spheroidal or spherical in shape. They show no peculiarity in them. Now, what causes the warm ionized gas to be ionized? So for that, we need to look at the BPT diagram of these galaxies. So here I am showing the spatially resolved BPT diagram for this particular red geyser galaxy. And the color coded and these are the points are color coded, the spaxels are color coded by their position in the BPT diagram, and we can see that an extended liner like or Seifert like line ratios exist throughout the galaxies. This means that the gas in the galaxy is mostly ionized by either evolved post AGB stars or shocks, or with probably some contribution from AGN. Okay, so let's talk about some of the properties of red geyser. First of all, the bisymmetric feature, which is of course the defining property. These are all red quiescent galaxies with no star formation in them. They have lots of cool gas present which could trigger star formation, but they don't. They have ionization consistent with liners or AGN. They also have interesting kinematics like high gas velocity and high gas dispersion compared to very low value of stars. And I'm going to talk about that in detail later, but they also have low luminosity radio AGN in them. So let's talk about that first. How do we know that these galaxies have AGNs? For that, we looked at VLA first radio continuum data to search for AGN. So we constructed a comparison sample or a control sample matching in global properties, and we found that the red geyser have a much higher detection rate compared to the control. So it's 20% versus 5%. But then we are looking for low luminosity AGNs here. So what we did is we also stacked the radio flux coming from the red geysers and controls. And this is what we found. We found that the red geysers have a much higher stacked radio flux compared to the control. So the details are in the paper. I'm not going into the details, but the bottom line is we found enhanced radio flux, and we concluded that these galaxies have low luminosity AGNs in them with an average luminosity of 10 to the power 23 watts per hertz. All right, so now, so these galaxies show a biconical feature that looks like a centrally driven wind. So the next question is, are these really AGN driven winds? For that, we turn to the kinematics. So the resolved velocity field looks something like this on the left. So here the red and the blue shows the redshift and the blue shift part of the galaxy. The values go up to 250 to 300 kilometer per second, and the gas kinematic axis always traces the bisymmetric feature on which is shown on the left in the small panel. The lower panel show the dispersion map or the gas dispersion map, which shows very high values with occasional clumps. They also we constructed a very simple toy wind model which has been described in Chung et al. And we find that the velocity field can very well be represented by this very simplistic wind model. So we obviously want to look at more detailed signatures. So our prediction from the wind model is as follows. So there is a bicone which is filled with warm gas clouds which are emitting emission lines. And all these gas clouds are moving radially outward. Now the observer standing on the right will see everything integrated along the line of sight. So even a spectra coming from the bottom is integrated along the cone volume in the line of sight. So what she sees is also a projection of this outflowing velocity. So a combination of this projection and integration would give rise to an asymmetric emission line. Not only that, the asymmetry should also switch from one side to the other. The center would, however, show a symmetric profile because there is not much cone volume to integrate over near the center. Here we used high spectral resolution Keck data to actually look for this signature. So we placed our Keck slit on top of the expected cone axis, and we extracted spatially resolved spectra along each of these spatial bins of 1 arcsecond pixel. And this is what we saw. So showing the H alpha lines, the lines are asymmetric, and it's asymmetric in the same way as we predicted of. So the red shifted part has a blue wing and a blue shifted part has a red wing. Now showing all the spectra coming from all the spatial pixels, starting from the bottom portion in the blue, representing the bottommost panel here, and as we go up, the different rows indicate the spectra from different spatial bins. The spectra is around the H alpha and N2 regions, and these are color coded by velocity. We can clearly see that the blue side has an asymmetry in the red wing, and the red side has an asymmetry in the blue direction. So this cone geometry, which predicts this systematic asymmetry, is confirmed by our observation, and we can say with confidence that these are actually winds that we are looking at, winds or outflows. So now I think the last and very brief point that I wanted to mention is about the fueling of these agents. So how are these radio agents fueled? Surprisingly, we actually detect quite a lot of cooler neutral gas in this galaxy. So here, showing the same 6 red geysers as before. Now the green panels show the cool gas traced by sodium D absorption line. And we see that there is a lot of sodium D present in these galaxies. And we actually detect this much cool gas only in geysers, but not so much in control galaxies. So in the left, showing the sodium D map, spatially resolved sodium D map coming from the red geyser, and in the right coming from the control galaxy, you can clearly see there is much more abundance of cooler gas in the red geysers. So that is one result, and the other one is now we looked at the kinematics of this cool gas to see what they're doing. And just a note, if an absorption line is in front of the galaxy is redshifted, it means it is inflowing into the galaxy. So redshift means inflow when we are looking at the foreground absorption line. So this is called down the barrel measurement. And we actually detect inflows in our spectra of sodium D. So here in the right, showing the stacked continuum subtracted spectra of sodium D coming from the red geyser sample shown by red and the control sample shown by different shades of blue. And we see that the red geyser sodium D show a very strong inflow or a strong redshift or a positive velocity. This means that we actually detect inflowing gas or signatures of gas accretion that is probably fueling the central AGN. So in summary, red geysers are relatively common Ori-type galaxy with ample amount of gas, but they show no amount of star formation. They're relatively common. They constitute 5 to 8% of the local red galaxy population. They host low luminosity radio AGNs in them, and they show optical emission and kinematic features supporting an AGN-driven wind interpretation. They also show signatures of inflowing cool gas, presumably feeding the radio AGN. We obviously still need to do more work on this, but these galaxies might be showing maintenance mode feedback in action in present time, and hence these are very exciting. I'm looking forward to your questions and all the discussions that we will be having in the future. Thank you so much for your attention.